Out recording. Hey guys, a lot of folks braved the weather. All right, I apologize. I'm not feeling great today, so I actually did fine last lecture, so I'll assume I'll do fine too. But I just sort of nod over it. That's why I'm just not feeling great. It's not the Rona. Yeah, Bernard. Let's talk about cache. Let's talk about sound caching. That sounds like a band name, huh? Sound cache, like a German punk band. Der Soundcache. All right. What are we talking about today? We're talking Rammstein. We're talking about basically we want to look at memory allocation using malloc, and we're going to Rammstein rocks. We're going to learn about, or at least start to look at memory allocation from the context of linked lists. And like for the next couple of lectures at least, we'll be kind of working in a kind of a listy environment, or we're working with linked lists, but also exploring how we manage memory within the application. And some things, like I'll gloss over some things today because we're going to hit them in a lot of detail later on. I'll try to get as deep as I can, if there are questions and so on. Actually, A1 had tons of questions, which was great. A lot of it was around stuff that we're going to talk about in detail later, but I'm happy to talk about it more than once. Why not? Why not? All right, linked lists and DMA. I got code over here somewhere. Code's up. Looks nice. And I have let's make sure I got a container running. Still running, nice. All right, here we go. Linked lists. We're sticking with structs, and mainly because it's kind of all we've got. There are no objects in C, so we're kind of just stuck with structs, which is fine. Like there's nothing wrong with the structure. We're going to start organizing them into data structures, and in C, and therefore in most operating systems, because most OSs are written in C, or at least can trace their heritage back to C. Like that's all we have is a structure. And so the underlying things in an operating system, the way the operating system handles processes, handles mapping memory into them, like context switching, all that stuff, everything is a structure. It's just structures. Somebody's going to do the meme for me. You mean it was structures all along? Always has been. Like it's just structs everywhere. So, and they're all linked together with pointers essentially. So we're going to kind of start to explore that. And as we explore more about linked lists and the various permutations of them and how to allocate that memory and free memory and so on, all those operations, that'll give us some insight into what the OS is doing as it's managing its own memory. And then from there, we can start to look at, well, what does the process itself look like in memory? What are the pieces of that? And how does the OS manage that? And I mean, this is not an operating systems course, but it's really here to prep you for an operating systems course. So we'll look at a lot of OS structures, probably not in the detail that Rich West would do, but in some detail at least. And it's also not a data structures course, so we're not going to go into all of the data structures and their runtimes and so on, but we'll see some. Like you'll play with a bunch of data structures. It's more of a practical application sort of course in that aspect, I think. So we're going to talk about linked lists. Like there's just all sorts of useful shapes for these things. And we're going to use malloc to manage the memory for them. Just what I said. This is mainly implementation stuff. All right, so here's our list. This is a list node. You guys can see this? Yes, you can. So here's a list node. Actually, don't need formatting, so I can shut that off. Like that. Make that a touch larger. Beautiful. Very nice. I'm going to use this term node all over the place, and kind of going forward in the course, I'll use that term. What I mean by node is just, it's like an item in a list or an item in a tree or a queue or something. It's going to end up being a struct because that's all we've got. So here's, for example, one of them. This particular struct, we're going to call it a node. Notice I'm type defing this. We talked about type defing last week. We'll pretty much do type defs going forward especially for structs like this, because it makes the code a little bit cleaner. There's no reason we can't say struct node every time we mean struct node, the type, but it's just so handy to type def it and use node instead. So all of our pointers and so on that are pointing to these things are going to be node pointers. But just keep in the back of your head that, oh, it was type def. It's really a struct node pointer is what we're talking about. So this is a basic, like this, you can't get much more basic than this one. It has a value of something. There's an integer in this case and a pointer, and that's it. Note what the pointer points to. What type is the pointer? It's a node pointer, right? So within this structure, which is a node, I've got a pointer to another node. And like the high level, what's going to happen is we're going to create these nodes on the fly. We're going to allocate memory for them. The operating system is going to give us a chunk of memory. We're going to take these pointers and point to those chunks of memory. And that's how we'll keep track of the nodes and link them together in different ways. Is it like a Java node? I don't know. Does Java have nodes? Sounds like a disease. Oh, my nodes are killing me today. Yeah, probably. But you know, yeah, you crack me up with the username, man. That's a great handle. Yeah, I guess. See, the thing about Java is I've never the data structures course here is in Java. Never made any sense at all to me. Like in Java, all these data structures like queues and lists and heaps and so on, they're all built in. Like you can just spin up a new one, give me a new list, new map or whatever, done. 210 really should be the first course in the sequence. You should take 210 first and then take 111 or 112, probably 112. Because in C, we don't have any of that. We have to build everything by hand. And you have to understand the underlying management of them in terms of memory and the process and so on. So that's like the intro to everything in computer science. The problem is that you learn all the structures, all the the data structures in Java. It's like, and then you come here, it's like, oh, why should I build a linked list like this? I can just say, give me a list. Well, it doesn't work that way. And most people would switch out if 210 was first. Yeah, I guess, Leanna. Yeah, probably. I'd change it a little bit. Isn't that what it's for, though? Isn't 210 the washout course, or is that 112? Not that anyone washes out anymore. Intro to CS weed out course, the WOC. What's 131, guys? Which one? Oh, pain. Discrete math? Are you shitting me? Oh, man. That's easy. Not that I can do it anymore, but I remember taking it. I took that course. It was easy. 330, yeah. You guys are such weaklings. All right, so here's our struct, right? Hardest since the 70s. Yeah, thanks. I should took it in the 90s. There. Although I started coding in the 70s, so there you go. All right, so this is our basic node. It holds some data and it's got a pointer to another node. That's it. And the thing about the data structures is like, once you see them, like once you see this linked list, you'll be like, what's the big deal? Like it's so simple. I don't know why everyone makes such a big deal out of data structures. And this thing we're gonna look at today, you just put in different shapes and you get, a queue or a tree or whatever you want. Like they're all linked lists. And so once you figure this out, it's like, oh, you got them all. And it's so simple. Like it's just not a huge thing. Did I start with C? Actually, no, I started with assembler. And from assembler, I went to C. I also did a ton of coding in PL1 on multic systems, some COBOL, C, all over the place at that point. Go-to statements. No, go-to hadn't been invented yet. Yeah, my first love is assembly language, but simple assembly language. I was writing 6502 and Z80 assembly, which is really, really simple. All right, so we're gonna create nodes on the fly. And guys in the chat, like talking about different languages, I think I said this first class, like once you know one language, they're all the same. Like they all do exactly the same thing. They have to. They're all running on the same hardware. Like the CPU only has a limited number of instructions, and all of the languages compile or interpret down to those instructions. So like they all, by definition, do exactly the same thing. It's just syntax. And we keep inventing languages for different industries or different fields to make it a little easier to think. Like I did a ton of Fortran programming. Why? Because I was in a scientific environment and we're doing differential equations all over the place. It's really easy to model a differential equation in Fortran, not so much easy to do it in C. So you just use whatever language has the syntax that matches what you're trying to do. Was an interesting computer. That was a hybrid analog digital computer. So it had a digital side like we're used to. It also had an analog computer on the other side. We used the analog computer to solve differential equations, simultaneous differential equations, because the computer just couldn't do it, didn't have the capability. But it's really easy to solve those problems in analog amplifiers and just read the value, which we do very quickly. So we use the analog side for the DiffEQ stuff and then the digital side for all the data processing. Those are the days, man. All right, here we go. I guess I got to get on this. Creating nodes. I'm starting to sound like that old gray-haired guy that I always hated in class. Creating nodes, we're going to do them on the fly. So to this point, we've been kind of creating things ahead of time. We've been setting up an array or an array of structs or a bunch of variables, whatever it happened to be. We've been creating them, we've been programming them essentially, and then when the compiler sees those, it creates memory for them in a special place in sort of the map of the application or the map of the program as it's running. I'll call it a process. That process has a memory location that's just set aside for kind of those predefined variables. So when I say int a equals 5, I wouldn't say a because it's a single character. But if I said int a equals 5, there's memory set aside for that integer. It's part of the process itself. It's kind of baked in. These things, however, we're creating these as we need them. So this is a runtime thing. I might have somebody on the keyboard saying, yeah, I want to add something to a list. Well, now I got to create a new node and link it into the list. That's being taken from a different set of memory. And we'll get into the memory management and how it's allocated and all the different parts in the program and so on. That's coming up in 2 or 3 weeks. For now, just remember that these things are being allocated from something called the heap. The heap is just a big bunch of unallocated memory that the process has, and I can ask for pieces of memory of certain sizes and then use them in my program. But it's a runtime thing. So this is kind of dynamic allocation. It's called, why we call it DMA, dynamic memory allocation. So the basic steps are, if I want to create something and add it to a list, I'm going to go and allocate memory for it. And then I'm going to fill in all the members, all the data in that node. And then I'll take that node and stick it into a list. But the first part, allocating, that's kind of the key part. Let's talk about that first. Yep. We're going to use malloc. Good old malloc, destroyer of worlds. It's going to return to us a chunk of memory. It might return to us a chunk of memory if it can. It's going to be of a specific size. Malloc, it's a function. It takes one argument. The argument, or at least the way we're using it, the argument is the size of memory that I want. There's some optional arguments that we're not going to worry about at this point. So malloc, we say, hey malloc, I want a struct size piece of memory. Maybe it's 40 bytes or something. Malloc goes to the heap, and the heap is just this unassociated memory, just in a big bowl, and says, okay, yeah, I got 40 bytes right here for you in a chunk. It returns a pointer to that chunk. So it essentially assigns that memory to us, because we requested this, that here it is. The way it gives it to us is in a pointer. It's a void pointer. We haven't talked about void pointers yet. A void means nothing, and so this is a pointer that doesn't have any type. It makes sense, right? Because malloc is just dealing directly in blocks of memory. Like, it doesn't know anything about types, it just knows memory. And why does it care what type it is? It doesn't. So it gives that chunk of memory to us, and then we have to shape that pointer into the correct shape for a node in our case. We're going to cast it. I had like 97 questions at this point in A1. You guys are really funny. I guess all the smart people came over to B. All right, we're going to cast this thing. Here's how I think about this. So this void pointer that's coming back from malloc, it doesn't have any shape. And the silly analogy I use for the heap and this kind of memory management, I just see, I see the memory as like cookie dough. I've got this big bowl full of cookie dough, and that cookie dough is all the memory, right? It's shapeless, like it's just dough and a big bunch of it. And I tell malloc how much of it I need. If I want to make a cookie, one cookie, I'm not going to take like a whole cup of cookie dough and well, I guess I could, it'd be a wicked big cookie, but I'm going to take, yeah, Jonas is like, of course you would. I'm going to take like, a couple tablespoons, right? A cookie amount of size of dough. That's why I give it a size. But then when it comes back to me from malloc, it's just still dough. It's kind of this blob of dough that doesn't have any shape to it. The cast, when I cast the pointer into a type, it's like a cookie cutter. So I got the shapeless dough from malloc. It's the right size, like it's the right amount, but it's not the right shape yet. So I take my cookie cutter and stamp out a cookie out of it. And now I've got a cookie that's the right shape, and I can make my cookie. So that cookie cutter is the cast, essentially. It's this. So malloc itself, this is going to return a void pointer to me, if it can. And then this is the cast part. I'm going to cast it into a struct node pointer. I'll have it typed up here, so I'm using struct node. And then I would assign this to something else. So I'd have a node pointer here. It'd look like this, right? Node pointer foo equals like that. So the cast operates on the void pointer coming back from malloc and then stores that value in foo. If you typed up it, you still need to say struct node. Bradley, I knew somebody's going to ask me that question. The short answer is I don't remember. I think you have to use struct node here. Like I mixed them here, right? So I've got node pointer foo, and then the cast here. I think that requires the actual type and not the typecast. If you want to know for sure, either look it up or post it on Piazza, and I'll go look it up and let you know. If you don't use a cast, so that, Jonas, that's a really good question. If I just do this, if I do that, that actually compiles, and it, as best I can tell, usually does the right thing. Like it sees that you're storing this in a node pointer, and so it kind of does the cast for you implicitly. My gut tells me that's implementation specific, Jonas. Like I think you can't be guaranteed that. So even though I see this sort of syntax all the time, where I sort of imply the cast, right? Because I'm storing it in a node pointer. It's like, oh, this thing's coming back as a void pointer. I'm storing it here, and so that casts it into the right shape for me. I get really nervous about that. Yeah, go ahead.
I mean, the way I understood kind of the necessity for like a type for pointers so far is so that we can use pointer arithmetic, right? So would it maybe would it be necessary if we have like an array of node structs, so to say, so that we can use pointer arithmetic? If it's just a void pointer, then it might not be able to know exactly the size of bytes, or something like that, maybe. But that's kind of the only reason why I've understood so far that pointers need a type, so we can use pointer arithmetic properly.
There's actually another reason here. The problem is that if I've got a void pointer, so it's shapeless, I don't know anything about the underlying structure. So that struct might have 17 variables in it. If I've got a void pointer pointing to it, there's no sense of where those things are, what they are, what their names are, anything like that. So I've got to cast the pointer into the right shape. That node, this cast, when I do that, the cast into a struct node pointer, that essentially gives me access now to that int and to that node pointer here. If it's just a void pointer, like I don't know where those are or what they are. So the cast gives me access to the internals of the structure. Can I recast it later? Yeah, you actually cast. So casting, here's the thing about casting. You're going to see a lot of casts in production code. Like if we popped open, some of the Linux kernel code, there's casts everywhere in there. Basically, you're reshaping something to something else. And it doesn't have to be like this. Like I could cast an int into a float or something. You can cast anything into anything else. The results of it, can vary, I guess. I get queasy with casts. And the reason is if something was like an int pointer when it began its life, like why am I casting it into something else? I mean, this is a special case, like a void pointer. We cast void pointers we almost always cast a void pointer because we need access to something that it's pointing to. And if it's not the right shape, I can't tell what's in there. But just sort of general casting, I see it a lot. I mean, we used to do it back in the day because like we'd have library functions, like a database library or something. And maybe that a function in that library was returning a certain type and we needed it to be in a different type for our application. Well, it's a library, so I don't have access to the source code. Usually libraries are shipped with just an object and the header file. I don't see the .c file at all. So I can't manipulate that code. All I have is what's coming out of the object file. So it's kind of a way to retrofit stuff that I don't have access to change the type. Windows programming, you're constantly casting stuff in Windows. Like if I'm doing Windows GUI programming, you're casting left and right, making stuff be the right shape. I just get really nervous about it because it just feels like I'm forcing something. And maybe that's just me, and the environments I was programming in. Yeah, thanks, Jonas. Cool, you guys are doing great. Yeah, so the whole thing about casting, I mean, you're going to see it all over the place, and you'll probably end up using it. Probably not so much in here, except for this situation where I'm casting a void, but you're going to run into it for sure. So obviously, if everyone else is doing it, it's not a huge issue. I just always was really nervous about casting because it just felt like I was trying to force something that maybe I shouldn't. And I prefer to like be really explicit about what something is. This is a node. I'm casting as a struct node. It's never going to be cast into anything else. So that's my thing about casting. I don't know. Where you're going to see it in here is mainly around this. When I'm doing a memory allocation, I need to cast the pointer into the shape of the thing that I'm pointing to. And so it's sort of to that, I don't know, Jonas or somebody else asked the question. So that works. That casts, you end up with a pointer that does the right thing. My suspicion is that might not work 100% of the time. It just feels like an implementation specific sort of thing. Or maybe it's something that C11 or something came out with that I just haven't run into. All of that to say that I guess I probably need to do some reading about especially C11, the latest version of C. Like what are they doing with casting? Was there any change to the language to make it a little simpler so I can do this and not worry about it? Because that's really clean, right? I love that. Yeah, I'm grabbing a node pointer out of this and doing an implicit cast into foo. I like that code. It just makes me nervous is all. When would it not work? When would not work? What not work, Olivia? The cast? Like this one? I guess what I'm saying, yeah, that. I guess what I'm saying is it works on my machine in my implementation of C. I'm not sure it's part of the standard. Because remember, all languages like C, JavaScript, Java, all of those languages exist as a specification. Like JavaScript, for example, there is no actual JavaScript language that anyone kind of produces. the language itself is text. It's a specification of what the language should do. And then each company that implements that language implements to the spec. They're all going to be slightly different. So it could be, this is just a guess, but it could be that this is an implementation specific thing for this version of C on this platform that whoever wrote this version of C did as a kind of a shortcut. I don't know if it's in the spec or not. I assume it is. I gotta go look at the stupid spec now. I try to avoid the spec because it's big and annoying. I guess I gotta go look it up though, huh? All right, for us though, just remember that what we're doing is we're calling malloc, give us a memory chunk the size of a node out of that big bowl of cookie dough. It's like get a node struct chunk that size, but it's still some kind of shapeless. It's just a blob. And then I hit it with the cookie cutter, which is the cast, and that puts it in the right shape. And now I can store that here and get to the value and the next pointer. Before, if it was just a void pointer, I couldn't. We'll actually see void pointers probably in another context. Like if we're using pointers to functions, for example, we're talking about this in A1, like having this kind of a side discussion of whether nodes should have some autonomy. Like should a node know how to sort itself if it's in a list that's going to be sorted? I kind of think it should. I don't think the list should know how to sort. The node itself should know how to sort, with others of its type, which means that it needs a sort function embedded in the node. The problem is that we can't put functions in structs. We can, however, put pointers in structs, and I can have a pointer to a function, because a function really is it's just a bunch of instructions sitting in memory, right? So I can have a pointer to the first instruction of the function. And if I've got several functions, let's say I've got a generic sorting list, and it relies on a function coming from the node to do the sort. Well, I'm going to write the list with void pointers because I don't know what kind of node it's going to use. It's going to have to take a look inside a node, grab the pointer from there, and then assign it to what was going to be a void pointer. So you'll see void pointers in that context at some point in the course, I think. You may have guessed that we're getting into the interesting part of the course, because now we're having like discussions about, stuff that's a little esoteric, I guess. All right, so we're going to cast it. So theoretically, I can make a library through a struct with function pointers. Yeah, why not? And then just have some code, like maybe have another function that you point to that chooses the correct function. That's kind of like your like the old calculator you did for PS1. Like instead of making all those individual function calls, you could have had an array of functions indexed into them and then used a pointer to that function to execute the function. So you really would only have one line of code to read that little, 5+2 or something. Just pop off the operator, use the operator as an index into your array. Like I would normalize them to 0. And then, and by normalizing to 0, I mean like if a plus is 32, or let's say it's 30, like everything starts, plus is 30, minus is 31, and so on. Just subtract 30 from those things so that a plus is 0 and a minus is 1. And when I saw the plus, it's an ASCII value, 30, 30. Subtract 30 from it, I get 0. That gives me a 0 index into an array. And what's sitting in that array location is a function pointer. And that's the function I'm going to run. So I could devolve that down into, deconstruct it down into just one line of, or a couple of lines of code to pick out the operator and index into that array. All right. Because it got real quiet there. I stunned you. All right, so malloc. Malloc is our friend here. Malloc. Can I make you a little bit bigger so I can read you? Sweet. There's our lovely cookie bowl sort of analogy. I love analogies. What if we call malloc and he doesn't answer the phone? There's no memory. for some reason we've exhausted the heap memory, there's just no memory left to allocate, or there's some other issue, like who knows what the issue is, or for some reason malloc cannot allocate any memory to us, it returns a null. So malloc will return null if memory is not available. It means that there's a chance that memory was not available. So every time you use malloc, the very next thing you need to do is to check the returned pointer and see if it's null or not. If it's null, that means that I couldn't allocate memory and I got to do something else, recover in some way. And that's kind of application specific. Maybe I try again, hoping that like, still turn it off and turn it back on, hope it works. So just try the allocation again and maybe it'll work next time. I don't know. Or go do something else and come back and try, Why would you not be able to allocate memory? Well, Sergey, maybe it's a really big, like I'm doing data analysis. And I just run out of memory. You only get a couple of gig to begin with. Yeah, Ian too. Got to crack up every time I read that, Ian, your handle. Like maybe it is like a big data crunching application. Like you don't get infinite memory. You only get about 2 gig. Like generally speaking, well, I guess kind of you get 4, but generally speaking, each process, each running application only gets 4 gig of memory mapped to it. And that's it. That's all you get. And within that, you've got to have all of your program code. There's going to be a piece of memory that's set aside for pre-allocated variables. So if I do int a equals 5 in my code, of course I wouldn't because it's a single character variable, but if I did that, there's a portion of the running process, the application, the program, that's got a 5, it's pre-built. So that portion's the data portion, that holds all of the pre-allocated variables. That sits in a particular spot in memory. So I've got the code I need to run, I've got this pre-allocated stuff, then I need a stack. The stack is when I make a function call, and we'll dig into this in a lot of detail in several weeks, but when I make a function call, I'm essentially jumping to another place in memory, and I need to pass variables to another function probably. What happens is I create a stack frame on the stack, and again, we'll dig into this, but there's a stack that's kept. That stack frame is created at the function call invocation. Let's say I've got a recursive function like your powers of function, calculating exponentiation. If you screwed up the recursion and didn't have a base case, you would just keep calling that function over and over and over again. Well, in that case, every time you call a function, you're creating a stack frame. That's part of your allocated memory, but you only get that 4 gig. And so you just keep creating stack frames. The stack starts at the top, I think. So the stack starts at the top of your memory and grows down. The heap, on the other hand, heap stuff starts sort of toward the bottom and grows up. But if I keep calling a function over and over and over and over again, I keep allocating stack frames, eventually I'm going to keep building that stack up until it runs into my code and the program's going to crash. That's when you run out of memory. So like there's a limited amount of memory available, I guess is what I'm saying. And so unfortunately, we have to manage it ourselves. There's no garbage collector or anything. We have to manage this memory. So we assume that there are going to be cases where we've run out of memory and I just can't allocate any. And so we check for that every time. Just check the returned pointer coming out of malloc. If it's null, there was a problem. That's it. And then, it's your code, right? So depending on what you want to do, as I said, try it again, go away, try it later, who knows what's going to happen. That's up to you. Note that this is a runtime error. If you get a null coming out of malloc, and then you try to access that pointer, your program's going to crash. It will crash hard. Like it won't shut down. It'll just stop executing. And the reason is it goes back to that memory map. So if we look at the kind of the physical memory in the computer, it's split in 2 pieces. The bottom half of memory, and I'm talking like the memory in the machine in your computer, the bottom half is operating system memory. The top half is for user programs. Anytime you're doing like a system call, like a malloc or something, you're ducking down into the kernel space, which is the operating system's memory, and executing stuff there and then popping back out. That's fine. Like there's a mechanism to do that. But if I've got a null pointer that came out of malloc, tried to allocate something, there wasn't memory, so I got a null, and then I try to use that pointer, it's pointing to null, which is essentially 0. Address number 0 lives at the bottom of memory. It's operating system memory. And what happens is, so there's a little physical chip in your computer called a memory management unit, an MMU. It has a couple of inputs. It has on one side, it has a map of all of the memory that your running program has been allocated. So it knows a range of memory addresses that are for your program, your process. It then sees where you're trying to get to. I'm trying to access memory at a certain location. It compares those two. And if your access request is not in the range that you've been allocated, you're going to get an access violation. It's going to be a SegVO, segment violation, or a seg fault. There's a physical wire that goes from the memory management unit to the CPU. It's an interrupt line. Yeah, of course you got seg. We all have seg faults, you know? We all have our faults. This should be a computer science t-shirt, right? So you've tried to access location 0. The memory management unit says, holy shit, this guy is trying to access memory that doesn't belong to it. It raises an alarm on that wire that's going to the CPU. There's a pin on the CPU for that specific interrupt. The CPU, whatever it's doing, it stops dead in its tracks and says, I got to take care of this right now. And it goes and kills the process. It terminates it with prejudice. The very next machine cycle doesn't even get executed in your program. It just gets killed. The reason why is that if you've got a running application, a running program that is all of a sudden trying to work with memory that doesn't belong to it, you don't know what's going to happen next. It's gone rogue essentially. And so you just terminate it and, sort it out later. It's like shoot them all and let God sort them out, right? That's what the operating system is doing, is just terminating the program immediately so it doesn't execute even another instruction. Why? Well, let's say we let it go. It's like, oh, you're trying to access memory that's not allocated to you? Yeah, whatever. And it writes a value to that address. What if that address is owned by a program that runs the control rods on a nuclear reactor, and you just overwrote the maximum temperature that the reactor could be from 100 degrees to 10,000 degrees? Like, now what's going to happen? The program that's running the control rods, it just reads that value. It doesn't know that somebody else changed it, right? And now the core is going to melt down because you had some other program accessing memory it shouldn't. So that's why we terminate it immediately. But anyway, that's a runtime error. Your compiler will let you do it. It's like, oh, you want to use a null pointer? It's like, I don't care. I guess C assumes you know what you're doing. We're supposed to be the experts. It's like, oh, you know what you're doing. I guess you can. And so what happens is, like, even in testing, like, you may never hit that edge case where you've got a null pointer or a pointer to somewhere outside your allocation until it's in production. And then for some reason, somebody pushes a button or something, you get into that code branch where it's like, oh, now it's going to use that null pointer and it's going to crash. Or worse, it's going to overwrite somebody else's memory. That's when you get the call at 2 a.m. from your boss saying, hey, like, why did everything crash? Why don't you go fix that right now? Oh, in fact, there you go. So seg fault or a SegVO. Doop, doop, doop. All right, so let's look at this. This is exactly what we just said to do, right? So I got a node pointer. I'm casting what's coming back from malloc. Malloc's give me a size of node, chunk of memory, and then immediately if new node. If new node is null, that if statement will fail. So just make sure it's not null before we move on. Get used to using null. any time you're using pointers, which you're going to be using constantly from now on, anytime you're using pointers, if you're not actively using that pointer, set its value to null, always. I call it grounding the pointer. You'll actually see that term, and I think the book actually uses the term grounding also. It basically comes from electrical engineering. My undergrad degree is in electrical engineering, so we didn't have computers back then. So grounding a pointer is similar to grounding a circuit where you're essentially grounding to a potential of zero. Um, you're setting it to null, essentially. I use the term grounding because I have for 30 years. So if you ground your pointers, you're pretty much guaranteed that if you try to use it and it's grounded, now I'm trying to access null and it's going to crash the program. It's kind of it's a two-edged sword, right? Like I'm on purpose setting up a situation where if I try to use that pointer and I haven't assigned anything to it, the program's going to crash hard. But that's preferable to having it running in production and randomly overwriting memory locations because I've got a pointer to something that I shouldn't have. Like, I set up the pointer, maybe I freed that memory up and now I still got a pointer to it, but I'm using it anyways. Like, that's really bad, really bad. It's much better if the program just crashes. So it's one of those situations where we're sort of setting it up to fail because we want it to fail, but in a controlled way. We want a controlled crash and not just some random event to happen that we got to go figure out. Isel says, what happens if you go back and decide to add something else to the structure so the size of the node increases? You can't. Actually, I take that back. You can. You can. Well, you wouldn't. I don't think you could go back and change the actual struct on the fly, but you can reallocate memory so you can grow and shrink it as needed. We're going to be using with structs for this, but maybe I've got some other shape of thing that I need to be bigger or smaller, whatever. So I can reallocate memory to grow it or shrink it. George says, basically you want to put yourself in a position where you have compiler errors and not runtime errors. Well, actually, sometimes it's not a compiler error either, but the runtime error, I'd rather have it crash than continue to run and do bad things. So I want to be able to control the crash. So we're going to ground pointers. Always, always, always ground our pointers. I'm going to die here. Here we go. It's even worse if we do this. We'll talk about the free function probably on Thursday. But basically, free takes memory that has been allocated with malloc and puts it back on the heap for something else to use, some other function, whatever. No, there's no memory allocation here at all. Like here, I'm allocating the size of node, right? I'm casting it into a node pointer, storing it here, but then I immediately free it. I put it back on the heap, but then I can do that. That works perfectly well. And what we'll find out is that free does not affect the pointer. The pointer still has the same value in it before I did free and after. So that some node pointer is still pointing to that chunk of memory that was allocated, except we handed it back to the heap. And the heap might have reallocated that to somebody else, right? And so now I've got basically two things pointing at this, and this works just fine. But there's something else that's pointing to that memory also, maybe rewriting stuff in there. Why would the heap do that? Well, heap don't care. Heap's kind of the honey badger of structures. Like, hey, ask me for memory. I'm just going to give you some memory. No, that's not really any logic in there. It's just it's a bowl of cookie dough. How much intelligence does a bowl of cookie dough have? Where did I put that? Creating a list, blah, blah, blah. My analogy to that was, I thought I actually wrote it here, but maybe I didn't. Maybe I wrote it somewhere else. So here's my analogy to this. Let's say you have an apartment down south and you get a key to the apartment, right? And then you move out, but you make a copy of the key. So now somebody else moves in and they get the key to the apartment. both of you have a key to the apartment. You can go in anytime you want and change stuff around or take stuff away or put stuff in there, but so can the other person because they also have the key. So this situation on this slide, I got two keys to the same apartment. Only one person should have that key at the same time, but there's no mechanism. We have to do it manually. Everything is manual in C. Questions, so it still has the value stored at some node, but it can be overwritten later on. Andrew, exactly. And maybe even by some other code. We may just blindly like do this and keep going as if, we still have it, but we don't. All bad, it's all bad. So free doesn't change the value of some node, it just frees up the memory for somebody else to use. I've already been allocated to some other item. What's the right thing to do here? Free and then set that pointer to null, right? So really we should have done this. Should have done this. That. Because now what happens? When I try to do that, it crashes. Because now I'm trying to access a null pointer, and as we just saw, that'll crash the program. So again, anytime you're not using a pointer, I'm not going to use the pointer now because I just freed it, right? So anytime I'm not using pointer, I'm going to set it to null for protection, for your protection. There's a really nice little tool. Whoops. So we never want two pointers to the same thing. Actually, no, that's actually a really common thing to do, to have multiple pointers pointing at the same thing. In fact, in like 2 slides, we're going to see just that. We've got pointers pointing to the same spot. But remember, it's like C assumes we know what we're doing, right? So if we do have a situation where we've got pointers, 2 pointers pointing at the same thing, that should be by design, and got to make sure that I'm not screwing something up with those 2 pointers. Well, in fact, we're going to leverage that in like 3 slides. I see. That's nice. I see. There's a nice tool that most development environments give you to do code inspection. In C-line, it looks like this. Yeah. So, oh, there's my like keys to an apartment. It's a hard bug to find, right? Because it's a logic error. Maybe you won't see it for a while. For production code, we're typically using code analyzers for this kind of stuff to check. So for example, actually I've got code over here. I'll just run the analyzer on it. Where is it in list? It's probably in node. This is just a little bit of code to, actually there's the code. So here, same idea, right? I'm setting up, in fact, I probably use this for the slide. There's some node allocating the size of node, and then I free it immediately and then try to access it. So what I get out of that is, all I have to do is come over here, right click, and say inspect code. And it'll say, you want just this file or the whole project? Let's do this file in this case. Okay. It goes and looks at it, runs some semantics against it, and it comes up with these. So it's like, here's a warning, data flow analysis. Hey, look, right there, local variable some node might be pointing to deallocated memory. And when I click on it, it shows me that stuff over here. And I can look at it and say, you're absolutely right. Sure enough, it's pointing to deallocated memory. So that's a really good tool to use. Like I would suggest using it on your projects, your problem sets. Like if you forget, or if you don't quite get what we're talking about or whatever, it's like, and you have some issue, doing an inspection on it will help you find those issues. And then at least you can see, it's like, what does it mean? Maybe, oh, deallocated memory. Oh yeah, free doesn't manipulate the pointer, I remember. I do that constantly. Not freeing memory and forgetting. I run inspections on my code all the time. Like, why not, right? That tool's there. It's going to save my butt probably. So of course I'm going to use it. All right, sweet. Why doesn't it what, Jonas? Oh, why doesn't it crash? Is there a situation where we want to keep the pointer but free the memory? Never, that I can think of. Once you've freed the memory, you basically have no access to the memory. It's like moving out.
Yeah,
You've
but
moved out. Yeah, go ahead.
Yeah, like my question is, why doesn't free implement that, right? Because if it's something that we always want to do after we call free, then why isn't it implemented that way, right?
You would think, right? You would think it should. Maybe it returns something. Let's go see if it returns something. C free. Maybe it does return a value. Returns void. Yeah, so it doesn't return anything.
Because that's really weird
Why?
then, right? Because then, like, if you do it after every call anyway, you can just implement that call in the function, you would guess.
Yeah, and I mean, you could go about it two ways, right? So you could just remember that and work with that. It's like, oh, I know free doesn't return anything. And so do a free and then immediately set that pointer to null, ground the pointer. Or as you said, just write a function to free up that memory and it would do that for you. So pass in the pointer, call free on it, set the pointer to null, and then return the pointer. That's a lot of work though. I mean, it's easier to me just to free it. I know that free doesn't return anything. So just free the memory and ground the pointer. It's like one line of code. When we free memory, are the values that were there made null? No, those values actually still exist. And technically speaking, if I didn't do that, if I did that, that would probably work. Like, I'm almost certain that would work. Let's try it. I'm not going to try it. I'm almost certain that this would work. And the reasoning is that here I allocate it, here I free it, and then the very next line of code, I stick something in there. Well, that pointer still points to that chunk of memory. You know, I've got some values. This thing is typed to a node pointer, so it knows where those things are. Like I should be able to set that value of 2 with no problem. Like that would work perfectly well. Logically speaking, that's an error because I'm accessing stuff I shouldn't. But in terms of the actual running program, it would do that all day long. Maybe, maybe. What happens if I'm in a multi-threaded environment? So I'm using threads. What we'll see later on in the course, how to write threaded code. So maybe I'm in a threaded situation and this all this code's on one thread, right? So I do this, I do that, and then my thread blocks or the process gets pulled out or something. But between here and here, some other thread starts to run and it allocates memory and it happens to get that chunk. And then this thread starts back up and then does that. In that situation, yeah, now somebody else owns that memory. And now I'm in a situation of two keys to the same apartment. I'm overwriting some value that some other piece of the program should have been working with. So as in a lot of things in C, A, it depends, and B, you can shoot yourself in the foot so many ways because it's just raw instructions and good luck is what C says. Free says the memory isn't reserved anymore. Yeah, it actually returns it to the heap. The heap is a big structure, and we try to keep the heap in a certain shape. So as I put stuff back on the heap, at some point, the heap is going to reorganize itself so that it has like properly sized chunks and so on. So the heap really is a data structure that's kept by the operating system. Why do we need to say some node equals null? Doing that here it's the principle of anytime you're not using a pointer, ground it. So when I do that, now if I try to do this, that crashes the program, which is what I want to happen. The still points, yes. Well, at this point, no. So if I'd say null, then that pointer just has a null in it. At this point, the pointer's like that point. If I didn't do this, if I did that, oops, if I did that, here, some node still points to that byte of memory. And since it's shaped like a node, it knows where that value thing is. So after the pointer has a value of null, it cannot have any other value. Oh, sure. I could, like right after this, just do it again, right? Let me just push these down a little bit. Hang on. We could do this again. Let's see. Could do that. Actually, I just defined it up here, so I just have to do some node. So here I allocate it, free it, and then allocate another one. That's going to be probably a different chunk of memory with a different address. And then I can do that. Jenna says, if I just use malloc, it returns an address in the heap, right? So yeah, but it actually gets removed from the heap. I mean, the heap itself is, we'll talk about the heap in a lot of detail at some point soon, but the heap is just it's a data structure that maintains blocks of memory of certain sizes.
Right, okay, sorry, but further confusion because like we also talked about memory in CS112 where we talked about kind of memory allocation, right, with kind of the pointers, and the pointers, like the variables of the pointers were stored in the stack, but the pointers pointed to a location in the heap, so the objects were all stored in the heap and weren't kind of moved to the stack. So this is different in C then. Kind of the objects that are malloced, so to say, are moved into the stack frame and are not kind of just, the stack just does not just contain a pointer that points to some location in the heap. Does that make sense?
Yeah, I'll have to dig into that because my understanding of a heap, I'm not a Java guy. When I think of a heap, I think of a data structure of essentially it's a bunch of blocks of memory that are linked together. They're all of various sizes. And as I allocate out of the heap, I'm taking chunks of the heap away, and then I have to add them back to the heap. So like when I think of reconstructing a heap, and holy shit, this has been like decades since I thought about this. But normally you would, like, if I free something and put it back on the heap, I hand it to the top of the heap, and then the heap decides where to fit that block of memory. And at some point, as memory gets fragmented, as I keep doing allocations of especially small sizes, memory is going to get fragmented at some point. Like I'll have all these holes all over the place in the heap. And at some point, the heap will have to consolidate itself. And it does that by coalescing smaller chunks of memory into larger chunks and then storing those as larger chunks. So I see the heap as an active data structure that's constantly being reshaped as I allocate and deallocate. Maybe they talked about it differently in 112, or maybe I can't imagine it worked differently because it's the same operating system, right?
I would say, like, yeah, but okay, then I'll look into that because like where you can't just really give. I mean, I don't know how memory works like that, but right, but how do you just then kind of take a part of memory and just put it somewhere else so that we can use it? I know. Does that make sense?
Yeah, I think, yeah, I think I see your angle. I mean, the memory address is a memory address, right? So it's not going to move anywhere. It's
Yeah,
just no
right.
longer a part of. Yeah, it's just no longer tracked by the heap until I hand it back to the heap.
Oh,
So if I do the alloc, when I do a malloc, like the heap doesn't know about that memory anymore. Like it's removed from that data structure. And then when I free it, it's fed back into the heap, and the heap coalesces blocks of memory into the right sizes. So, I mean, the memory itself isn't moving, but the structure around it is changing. The way the heap sees that memory is changing, I think.
okay, that makes sense. But okay. But kind of from the visualization, from the stack starts at the top and the heap starts at the bottom, right? Then it's just kind of that just chunks of the heap are taken out from kind of, or like are moved up, or are, okay, I don't know.
Yeah.
But
Yeah.
okay,
You know what,
thanks.
Dennis? I'm going to push that discussion off because we're actually going to look pretty deeply into the heap.
Yeah.
And we can talk about that then.
Yeah, sorry. Thanks though.
Yeah, no worries. All right, let's keep moving on because I got to talk about lists too. What time is it? Oh, jeez. Let's talk about lists. We'll talk about heaps in nauseating detail soon. Let's create a list. Lists are like so simple. I don't know why everyone makes such a big deal out of a linked list. It's like there's nothing big about them. Let me just delete some stuff here again. We were playing around with this in the other lecture. I'll copy this. All right, this should be what's in the PDFs pretty close at least. And this I'll delete. All right, so this is a linked list. That's it. If you understand this shape, you've got it. And frankly, if you understand this shape, you understand all of the other structures we're going to use. Trees, queues, stacks, all of them. They're just this. There's nothing fancy here. This is that struct, right? So I got a value. Where's my struct? Here, I'm in 16. It's this one. There's my value and a node pointer to next. So here it is. There's that value. There's the next pointer. Next pointer is going to point to one of two things. It's either pointing to another node, in which case it's got a memory address on it, or it's pointing to null, in which case it's the bottom of the list. That's a linked list. There's nothing magic about this. When I do a malloc for one of these things, so I do a malloc for the size of one of these structures, what I get back is a pointer to that structure. That's what goes in here. Let's talk about traversing, and maybe it'll make sense. Let's say I've got an empty tree, empty list rather. So this code uses a pointer called head. Now let's go back to this picture. Let's talk about that. So head is always going to point to the first node in the list. This is a singly linked list. And in other words, it has pointers that just go in one direction. A doubly linked list would have pointers pointing up as well. But we're doing singly linked here. So it's just pointing downward to the next node. Head is always going to point to the top. And I can't recall who asked it, but this is a situation where we're going to have multiple pointers pointing to the same thing, which is fine. Like this, it's just a memory address, right? And it's just how we use them. So let's talk about head. If head is null, because remember, when I create a pointer, what's the very next thing I do after I create a pointer? I set it to null, right? If I'm not using it. So in an empty list, that head pointer is going to be null. There's not going to be anything there yet. So it's pointing to null. If it is null, and let's say that this looks like it's part of a function that creates a list for me out of a node. So I've passed in a new node. Well, if the head is empty, that means there's nothing in the list. Then just take that node and point head to it, and that's it. Now I'm here, basically here. If it's not null, that means there's already a node in the list. So now I'm down in the else. Now I'm going to have this little pointer called walker. The very first thing I'm going to do is point walker to head. Copy, paste. Oops. So let's bring this guy down here. Pointing walker to head does this. Does this. So if walker and head are equal, they have the same address in them, they're pointing to the same place, right? That's what's happening right there. So we're starting at the top of the list each time. And now all I have to do, yes, it's a node pointer. There's code above this that you don't see, Bernard. So walker and head are both node pointers. So I just set walker to head. So if that situation, next, I'm going to have a little loop. And what I'm interested in here is I'm going to look at walker next. So let's look at walker next. Walker next actually has a value here, right? It's pointing to this node down here. So it's non-null. If this were null, we'd just skip down, but it's not null yet. So walker next is not null. We're going to set walker to that value. So walker next, non-null, it's got an address in it. Set walker to that address. What's that address pointing to? This guy. So now walker looks like that. Yeah, I'm just tracing the list down. You got it, Ian. What do I do next? I'm still in the loop. Is walker next null? Walker next is null. That tells me I'm at the bottom of the list. So if I want to add a node to this list, now I just say, all right, so walker next is null. I'm going to fall out of the while loop. Now I'm going to set walker next to whatever the address of the new node is. Here's my new node over here. I'll just copy one. Here's my new node. So Walker next, this value is now not going to point to null anymore. It's going to point to the address of the new guy this way. Oops, I want that copied. This one. So next now is pointing to this guy, and this guy's next is now null. It's null because when you set up a node, I'm not using a pointer, right? So what do I do with the pointer? I set the pointer to null. And then we're out of this little if statement. So all it does is start at the top, looks at the next value. Is it null? Nope. Set Walker to that value. Now I'm looking at this guy. Is he null? Yes. Place, here, change that from a null to the address of this new guy down here. That links it in. This guy already has a null there. The next time I add something to this list, I start at the top, keep walking down, find the null, place the new guy at the bottom. So that's all we've got to do. Cool, huh? That's a linked list, guys, at least adding something. What if I want to find something in the list? What do I do? Exactly the same thing, right? Except here, while Walker equal next, I also have a line that says if value equals the value of the thing I'm looking for. And if I do, find it, return the address. And I've got the address of the node. All of them work that way. If I want to count the number of nodes, start at the top, count them as I go down. If I want to find something, start at the top, go down until I find it. If I want to add something to it, start at the top, go down until I find the null, add it at the bottom of the list, and I'm done. Here's if I'm looking for something, it's the same code. In this case, so if head's null, and I'm looking for something in a list, if head's null, then the list is empty. And I just say it's empty and I return a null. Otherwise, same code, start at the head. Well, I've got Walker, go look at the value. And if it's the thing I'm looking for, just return that node. That Walker is a pointer to that address or a pointer to the node. Otherwise, go to the next one and look for the value there. That's how I find stuff. Other structures, stack, it's a linked list, except my operations are all at the top, pop, push, peek, and so on. I'm just working at head essentially and manipulating those nodes instead of walking all the way down. I just work at the top. A queue, exactly the same thing. I insert things on one side, so I got a head and a tail. I insert at the tail, I watch for them at the head. As I remove stuff from head, that stuff moves up in that queue, right? Priority queues, the same thing. Just have a bunch of queues all sorted by some value and then feed into one queue. They're all just queues. They're all linked lists. Binary trees, it's a linked list, except instead of one pointer, I got two pointers left and right in a binary tree, and probably a third one pointing to my parents. But it's exactly the same thing. We manipulate them exactly the same way. All these structures are the same. It's just, that's why you see them everywhere, linked lists. Like once you figure out a linked list in a in whatever language, like now you know all the structures. Binary trees, binary trees are fun. Red, black trees and all those AVL trees, I love those. Oh, did somebody finally post that, Liana? I asked him in A1 to post it, the structs or this thing. All right, I got one more minute. I'll briefly say this. I'll say it again on Thursday. So just to put it in your head, because I got the minute. Oh, yeah, it always has been. I tend to think of list and node as separate things. They don't know about each other. The node doesn't know it's in a list. The list doesn't know what's in a node. It just does listy operations. The node does nodey operations. They're two separate things. They work together. I can hand a node to a list and ask the list to add the node to the list. It'll do it. Delete the node from the list. It'll do it. It doesn't know what's inside the node. Nuts, I'm out of time. This actually led to a really deep discussion in A1 about like thinking organizationally like this and trying to have kind of abstract or agnostic objects that work sort of on anything. And I'd actually like to have that discussion in here too. So I'm going to put that off till Thursday. We might start Thursday in here on that discussion. This is like a 2-minute discussion or 5, but I think it's really interesting to talk about. So that's what we'll do first thing on Thursday. Bottom line, we use pointers and structs all over the place. All right, I will see you all on Thursday. See you Thursday. Thanks for coming, guys.
Professor,
See ya, see ya.
Professor, can I ask you a question?
Maybe. I don't have a lot of time. What do you got?
It might be a stupid question, but to be honest, I'm just still a little bit confused about pointers. So would it be correct to say that when you create a pointer for an array, that pointer is similar to a walker with the linked list? I mean, in the way that we use it.
Yeah, Sergey, I only heard about half of that. I think it was something about a pointer to an array.
Yeah. Can you hear me better now?
No, not really. Can you post it on Piazza? It's just the acoustics in here are really weird with the speakers.
Yeah, okay.
Yeah, just take it up on Piazza. Actually, so everyone can benefit. All right, see you guys. Thanks for coming.